We live in a universe that is full of bright objects. On a clear night, one can see thousands of stars with the naked eye. These stars occupy merely a small nearby part of the Milky Way galaxy. Telescopes reveal a much vaster realm that shines with the light from billions of galaxies. According to our current understanding of cosmology, however, the universe was featureless and dark for a long stretch of its early history. The first stars did not appear until perhaps 100 million years after the Big Bang, and nearly a billion years passed before galaxies proliferated across the cosmos. Astronomers have long wondered, how did this dramatic transition from darkness to light come about? After decades of study, researchers have recently made great strides toward answering this question, thanks to the James Webb Space Telescope. In an awe-inspiring effort to seek the first stars, the Webb telescope has captured the farthest star ever detected in the very distant universe, revealing hidden fundamental chapters of cosmic history. Join us as we dig deep into how James Webb just shed light on the earliest stars in the cosmos. "400,000 years after the Big Bang, the universe was a cold, dark fog of hydrogen and helium atoms. Less than 400 million years later, it had begun to shine with the light of infant galaxies. Sometime in between, the first stars must have formed. Astronomers know that the first stars, officially known as population 3 stars, must have been made almost solely of hydrogen and helium, the elements that formed as a direct result of the Big Bang. They would have contained none of the heavier elements like carbon, nitrogen, oxygen, and iron that are found in stars shining today. In other words, population 3 stars were metal-free. This might seem like a bold statement given that we have not actually observed any metal-free stars. But as with all scientific claims, it is based on evidence and reasoning. We know from observations, experiments, and calculations that only hydrogen and helium and minute amounts of lithium were formed directly after the Big Bang. The only way that heavier elements like carbon, oxygen, and iron can form is by fusion of lighter elements in the cores of stars. So until the first stars began to form them, none of these elements existed in the universe. The first stars must have been metal-free. Although astronomers are quite certain what the first stars were made of, they are less sure how massive they were. Strangely, one constraint on the mass of metal-free stars comes from what we don't see. Because we haven't observed any metal-free stars, we are fairly certain that there could not have been many small ones. Small stars like the Sun last for billions of years. If small population 3 stars were common, we should have detected some by now. Extremely large stars, on the other hand, burn their fuel very quickly. A star 60 times the mass of the Sun lasts less than 1 million years. If all of the first generation of stars were extremely massive, none would still exist, and it would make sense that we have not seen any. Additional evidence for the size of the first stars comes from computer models that simulate how large clouds of hydrogen, helium, and dark matter could cool and collapse to form stars in the early universe. These simulations also suggest that it takes a lot more matter to form a metal-free star than one with even a small proportion of metals. Combined with the fact that we have not seen any metal-free stars, this leads many astronomers to think that the first stars were probably very massive, perhaps ranging between about 10 and 300 times the mass of the Sun. The temperature and brightness of a star is directly related to its mass. The more massive the star is, the hotter and brighter it is. If the first stars were very massive, they also must have been extremely hot and bright. A star 100 times the mass of the Sun, for example, would have a surface temperature around 100,000 kelvins and would shine with the energy of 1 million suns. If the first stars were this hot, they must have been giving off enormous amounts of high-energy radiation. While the Sun emits most of its energy in the optical part of the electromagnetic spectrum, the visible light that we are all familiar with, almost all of the light emitted by a star with a temperature of 100,000 kelvins, would be in the form of ultraviolet light, which is invisible to human eyes. Astronomers think that it was the ultraviolet radiation emitted by the first stars that began to ionize the universe, lifting the fog of opaque neutral hydrogen that filled the universe during the so-called Dark Ages. Based on what we know about physics, we know that if any of the earliest stars were smaller than 0.9 times the mass of the Sun, they should still be shining today. But if they were very massive, they would have had extremely short lifetimes, burning up their fuel quickly and dying within a few million years of forming. What exactly happened to them would depend on their mass. Computer models show that stars greater than 10 and less than about 140 times the mass of the Sun would have ended in supernova explosions, the metals that formed in their cores blown out and dispersed into the surrounding universe. The remains of these stars would have collapsed to form neutron stars or black holes. Larger metal, free stars, up to about 300 solar masses, might have exploded in a strange type of supernova. These explosions would have blasted every bit of the star out in all directions, leaving nothing behind, no neutron star or black hole. The only signs of these stars would be found in the chemical composition of later stars that formed from their exploded remains. Even larger metal, free stars would have collapsed directly to form black holes, taking everything with them without even exploding first. While these stars would not have contributed matter to form new stars, they may have influenced galaxies in other ways. It may be that these black holes were the seeds of supermassive black holes found at the centers of galaxies today. So far, the only real evidence we have for the first stars is in the tracks they've left behind, the metals they formed that we see in later generations of stars, the effects of their ionizing radiation on the primordial gas in the universe, and perhaps their remnant black holes. If the first stars were massive and short-lived, any that existed nearby are long gone. Even if they no longer exist, it is theoretically still possible to see them. Telescopes like Hubble allow us to see billions of light-years away, and thus billions of years back in time. The James Webb Space Telescope gives us the advantage of being able to detect even dimmer infrared light. Although most of the light given off the first massive stars was in the ultraviolet part of the spectrum when it was emitted, the universe has expanded so much since then that much of it is now in the visible and infrared. And in an inspecular effort to seek the most distant stars, the Webb Space Telescope has captured the farthest star ever detected in the very distant universe, within the first billion years after the Big Bang. Webb's near-infrared camera instrument reveals the star to be a massive B-type star, more than twice as hot as our Sun, and about 1 million times more luminous. With this awe-inspiring discovery, James Webb could fill in long-standing gaps in our knowledge, allowing us to finally see exactly how the universe transitioned from a formless expanse of churning plasma into the familiar arrangements of galaxies, stars, and planets that grace the sky. The star taken by James Webb has a technical designation WHL 0137 LS, but scientists prefer to call it by a much catchier name, Earendel. Fans of the author John Ronald Reuel Tolkien, famous for fantasy novels, including the Lord of the Rings series and the Silmarillion, might already find this name familiar. And, as NASA astronomer Michelle Thaller confirmed, the name is truly inspired by Tolkien's fantasy writing. In Old English, Earendel is a personal name, but it also can mean the morning star or the dawn. In The Lord of the Rings, Earendil is a half-elven character who travels the seas carrying a jewel, a Silmaril, called the Morning Star. According to Thaller, WHL 0137, LS is the first star, the farthest star we've ever seen. So Earendel is a beautiful name for it. However, a star as brilliant as Earendel would be impossible to see from Earth given the vast divide between the two. The star is located in the Sunrise Arc galaxy and is detectable only due to the combined power of human technology and nature via an effect called gravitational lensing. Both Hubble and Webb were able to detect Earendel due to its lucky alignment behind a wrinkle in space, time created by the massive galaxy cluster WHL 013708. The galaxy cluster, located between us and Earendel, is so massive that it warps the fabric of space itself, which produces a magnifying effect, allowing astronomers to look through the cluster like a magnifying glass. While other features in the galaxy appear multiple times due to the gravitational lensing, Earendel only appears as a single point of light even in Webb's high-resolution infrared imaging. Based on this, astronomers determined the object is magnified by a factor of at least 4,000, and thus is extremely small. The most distant star ever detected, observed 1 billion years after the Big Bang. The previous record, holder for the most distant star, was detected by Hubble and observed around 4 billion years after the Big Bang. Another research team using Webb recently identified a gravitationally lensed star they nicknamed Quiller, a red giant star observed 3 billion years after the Big Bang. Stars as massive as Earendel often have companions. Astronomers did not expect Webb to reveal any companions of Earendel since they would be so close together and indistinguishable on the sky. However, based solely on the colors of Earendel, astronomers think they see hints of a cooler, redder companion star. This light has been stretched by the expansion of the universe to wavelengths longer than Hubble's instruments can detect, and so was only detectable with Webb. Webb's near-infrared camera also shows other notable details in the Sunrise Arc, which is the most highly magnified galaxy yet detected in the universe's first billion years. Features include both young star-forming regions and older established star clusters as small as 10 light-years across. On either side of the wrinkle of maximum magnification, which runs right through Earendel, these features are mirrored by the distortion of the gravitation lens. The region forming stars appears elongated and is estimated to be less than 5 million years old. Smaller dots on either side of Earendel are two images of one older, more established star cluster, estimated to be at least 10 million years old. Astronomers determined this star cluster is gravitationally bound and likely to persist until the present day. This shows us how the globular clusters in our own Milky Way might have looked when they formed 13 billion years ago. Astronomers are currently analyzing data from Webb's near-infrared spectrograph instrument observations of the Sunrise Arc galaxy and Earendel, which will provide precise composition and distance measurements for the galaxy. Since Hubble's discovery of Earendel, Webb has detected other very distant stars using this technique, though none quite as far as Earendel. The discoveries have opened a new realm of the universe to stellar physics, and new subject matter to scientists studying the early universe, where once galaxies were the smallest detectable cosmic objects. The research team has cautious hope that this could be a step toward the eventual detection of one of the very first generation of stars, composed only of the raw ingredients of the universe created in the Big Bang, hydrogen and helium. Another stunning image from the James Webb Space Telescope also has given scientists a stunning look at the dusty belts of debris surrounding one of the brightest stars in the night sky. Similar to the asteroid belt in our own solar system, these orbiting rings of shattered rock and ice can help reveal how planetary systems form. The debris disks orbit Fomalhaut, a star that is younger and bigger than the Sun, about 25 light-years from Earth. One of the brightest stars in the night sky, Fomalhaut glows in the southern constellation Pisces Austrinus. While two belts had been observed around Fomalhaut before, the new image published today in the journal Nature Astronomy shows that 3 belts encircle the star. I don't think anyone can look at that image and not think, "Wow, that's gorgeous," says Alicia Weinberger, an astronomer at the Carnegie Institution for Science in Washington, D.C., who was not involved in the study. Fomalhaut is famous among astronomers because it has one of the first belts ever spotted outside of our solar system. In the 1980s, researchers using the infrared astronomical satellite serendipitously discovered debris belts around a few stars known as the Fabulous Four, Fomalhaut, Vega, Beta Pictoris, and Epsilon Eridani. The Fomalhaut system became even more intriguing in 2008 when astronomers using the Hubble Space Telescope detected what appeared to be a massive planet orbiting the star. Fomalhaut b was the first exoplanet directly observed in visible light. But it seemed to vanish in later observations, and in 2020, Andres Gaspar of the University of Arizona led a study that found the object was likely a cloud of dust billowing out from a collision between two smaller objects. Gaspar has been waiting for years to get a closer look at the Fomalhaut system with the Webb telescope, the biggest space telescope in history. He began designing a program to look at the star with Webb's Mid-Infrared Instrument, or MIRI for short, in 2016. The telescope finally launched on Christmas Day in 2021, and in October 2022, Gaspar got his chance to revisit Fomalhaut. It paints a very different picture from what we assumed we would be seeing, Gaspar says. It's really exciting. We see a very complex and very dynamically active system. Around the Sun, the asteroid belt and more distant Kuiper belt contain the leftovers of the solar system. Asteroids, comets, planetesimals, and other ancient debris that was not incorporated into the planets. There should be debris disks circling thousands of other stars, but observing those faraway belts of smashed-up space rock is no easy feat. MIRI captures mid-infrared light, which the human eye cannot see. This type of light is especially useful for observing dust. Previous space telescopes also had mid-infrared instruments, but MIRI's aperture is much bigger, which means it can collect more light and resolve fainter objects. It's unprecedented, Gaspar says. And I don't think we're going to see anything like it again in my professional career for sure. It is really a once-in-a-generation opportunity for astronomers. Using MIRI, Gaspar, and his colleagues saw that the Fomalhaut system not only has an inner disk like the asteroid belt and a big dusty outer ring like the Kuiper belt, but also a fuzzy intermediate ring. The gaps between the rings, as well as their misalignment, suggest that there are unseen planets orbiting the star that are too small to be observed. It's so cool to finally see all of the structure inside the main dust belt that other telescopes have never been able to see before. So I was just really excited, says Samantha Lawler, an astronomer at the University of Regina in Saskatchewan, Canada, who wasn't involved in the new research. I could spend a lot of time just staring at that image. The intermediate belt was a surprise, she adds, because previous images hadn't shown anything there. It fits really well with the theory that Fomalhaut b, the exoplanet candidate, is a dust cloud from a collision, because there is a bunch of stuff at this distance that Fomalhaut b would have had to come from, Lawler says. The dust in that intermediate ring hasn't been lingering for 400 million years, the estimated age of Fomalhaut. It would have to be constantly regenerated from collisions between asteroids and comets, and the study team believe that they may have spotted another dust cloud from a collision that is in the process of expanding. This great dust cloud was spotted in the outer belt, and its size, as well as the size of the dust grains reflecting light to the telescope, suggests the cloud came from a collision between two planetesimals, each about 450 miles wide. We expect collisions to take place in debris disks, says astrophysicist Meredith McGregor of the University of Colorado at Boulder, who was not involved in the study. Small dust grains are removed on timescales shorter than the age of the system, which means that the dust we see today has to have been regenerated through collisions. But we do not regularly resolve individual collision events, she points out. It's critical to make sure that it is in fact associated with the system and not a background object. The findings are thrilling researchers who have been waiting to see what new possibilities James Webb opens up. Like McGregor says, it's amazing to see the quality of the data and think about what other new science we will be able to do. As a piece of breaking news, NASA has just launched its first mission to a mysterious world made largely of metal, on a journey to find out whether the asteroid is the exposed core of an early planetary building block from the beginning of the solar system. The Psyche mission lifted off at 10:19 a.m. At Friday aboard a SpaceX Falcon Heavy rocket from NASA's Kennedy Space Center in Florida. Psyche will be the first of many upcoming NASA science missions slated to launch aboard the Falcon Heavy rocket. According to David O., Psyche Chief Engineer for Operations at NASA's Jet Propulsion Laboratory in Pasadena, California, the mission, named for the 16 Psyche asteroid it will observe, will travel about 2.2 billion miles, 3.6 billion kilometers, over the next 6 years to reach the space rock, located in the outer part of the main asteroid belt between the orbits of Mars and Jupiter, said David O., Psyche Chief Engineer for Operations at NASA's Jet Propulsion Laboratory in Pasadena, California. Scientists believe the large M-type or metallic asteroid could be the exposed core of an early planetary building block and may resemble the cores of rocky planets in our solar system, such as Earth, Mars, Venus, and Mercury. The core may have been exposed due to violent collisions with other rocky bodies early in the solar system's formation. Ground and space telescopes have observed Psyche in the past, mainly detecting radiation bouncing off the reflective metal on the asteroid's surface. Together, these observations have helped scientists develop a model of the asteroid's shape, which is about the size of Massachusetts without Cape Cod, and a surface area equivalent to California. Elkins, Tanton said, but even using the Hubble Space Telescope, Psyche only appears as a few pixels. Like Elkins, Tanton said, we do not know what Psyche looks like. I always joke that it's shaped like a potato because potatoes come in many shapes, so I'm not wrong. But we're going to find out when we get there. The spacecraft's instruments will help scientists determine the asteroid's chemical and mineral composition, topography, mass, gravitational field, and rotation. The mission's magnetometer will attempt to detect evidence of a magnetic field around Psyche, which could suggest that the space rock initially formed as a planetary core. Psyche, which has a high density, is largely made of iron and nickel, along with something else, which may be rock, sulfur, or carbon-based, Elkins, Tanton said. If Psyche isn't a core, it could be a rare leftover object from the formation of the solar system that has never been observed. The other idea is Psyche is a kind of primordial, unmelted body basically formed from the very first materials in the solar system that came together under gravity and was preserved in this primordial state ever since, said Ben Weiss, Psyche Deputy Principal Investigator and Magnetometer Lead. Weiss is a professor of planetary science at the Massachusetts Institute of Technology. Psyche may have formed near the Sun and then was reduced to metal over time as oxygen atoms were stripped away from iron atoms, an object hypothesized but never found. The science team is eager to see the surface features of the asteroid. Radar indicates that there are 2 large craters on the surface. But what does a metal crater look like? Psyche may have little metal spikes, spires, and even tiny pieces that resemble a type of metal sand within the crater, said Elkins, Tanton. It's also possible that Psyche experienced volcanic eruptions, creating huge cliffs and greenish-yellow lava flows due to their sulfur content. As Elkins, Tanton said, this is our scientifically motivated idea, almost certain to be completely wrong. It's going to surprise us when we get there. I think there's a very good chance that it's going to be outside of our imaginings, and that is my fondest hope. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode. Subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.